Hello, this is Sam Lim from the University of California, Irvine, and I will introduce our work, Durin, the first solution to leverage for clustering large low-dimensional data with a realistic scale via CPU FPGA heterogeneous platform. Clustering is actually one of the fundamental tools of unsupervised machine learning, and the various classes of clustering algorithms, such as k-means, division, and affinity propagation, have been successfully applied to many important applications. Because existing work related to clustering has shown that the distance metric dominates the runtime of typical clustering algorithms by over 70%, FPGA-based hardware acceleration has been successfully applied to many clustering algorithms to improve high performance and power efficiency. However, the problem is that the acceleration techniques have not successfully extended to large low-dimensional data, and no published accelerator has outperformed the state-of-the-art software due to these two reasons. First, indexing structures like KD trees are actually vital to reduce the problem space on low-dimensional data, but it's quite difficult to accelerate because it needs higher clock speeds and advanced caches like CPU have. Also, implementing indices on accelerators diverges resources from the main bottleneck, which is distance calculation. And the other reason is that the performance is limited by slow PCI access to host memory for the terabyte scale sizes of real-world data sets of interest. To overcome these hurdles, we presented Durin, the first CPU FPGA heterogeneous system architecture solution for both large and low-dimensional data. Before discussing Durin's specific contributions, I wanted to underline that, as you can see in this figure at the bottom of the slide, Durin completely implements the quadtree index and algorithmic control in host software to leave most of the FPGA resources for computation-hungry distance calculation. The key innovation of Durin is its hardware-software co-designed quadtree modification to efficiently partition the clustering algorithm across the CPU FPGA heterogeneous system. And our specific contributions are mostly focused on not introducing a prominent new bottleneck, such as PCI performance limitation and the computation overhead placed on the CPU. So first of all, if the size of the dataset exceeds onboard memory, storing the dataset in the host side memory and getting the data via PCIe is inevitable. So in this case, PCI bandwidth will be one of the most prominent components, giving us a performance bottleneck. So the first software hardware co-optimization point is implementing a configurable threshold parameter to adjust depth of index structures on the software, and a novel variant of the lossy GFP block floating point compression scheme on the hardware side. To hide the PCI latency, we implemented an asynchronous distance calculation interface between software and hardware. However, in this kind of scenario, if the CPU consumes a lot of time for the tree traverser, the effect of the asynchronous interface is going to be decreased. So the final point of co-optimization is implementing a conservative neighborhood bounding box for collision detection, which is much simpler than a hypersphere-based collision detection scheme. Okay, from now on, I will briefly explain our dreams architecture. This figure shows the overall heterogeneous architecture. The data for clustering exists only in compressed format on the host side memory, and they are decompressed on the fly at the accelerator side before computing the distance metric. This design takes advantage of the fact that the only hardware accelerator needs to look at the low data for distance calculation. The index and cluster states are stored in an uncompressed format because the software also needs to access them. And our prototype of Durin is implemented for the Diviscan clustering algorithms with Haber-Sein and Euclidean distance metrics. In the case of the clustering algorithm, it is run by host software in multi-threaded mode for faster clustering. The first step in implementing software hardware co-designed quadtree is to overcome PCI bandwidth limitation, as I mentioned at the beginning. In the case of software side, Durin uses the quadtree and divides the space into four sub-quadrants recursively by the mean coordinate of all points in the current quadrant. The configurable threshold parameter for the minimum number of points in a quadrant is a newly introduced parameter by Durin, and this parameter matches with hardware side optimization, which is a novel variant of lossy floating point compression algorithm, GFPE, to overcome PCI bandwidth limitation. This parameter's goal is to allow more efficient block floating point compression within each leaf by collecting larger blocks. The original GFP low-G floating point compression algorithm is very efficient, but not quite fit to be used in hardware because of its sequential characteristic. So we modified the original one-dimensional GFP compression algorithm, which actually uses four elements in the block and compresses the value block by block, as it can be accelerated by hardware. Durin's design point two is implementing an asynchronous interface across multi-threads to hide PCI latency. As you can see in the right side figure, each thread in the thread pool maintains many current cores and send distance calculation from each border point in independent asynchronous batches. As long as a sufficient number of core points exist, PCI latency will not become the bottleneck. However, one single batch takes a long time due to the tree traversal, then this potential software tree traversal bottleneck causes the accelerator to stall, and it's going to be meaningless for implementing an asynchronous interface to hide PCI latency. So based on this insight, Durin's design point 3 would be targeting to minimize CPU overhead, especially tree traversal overhead. When traversing the quad tree, the algorithm must determine whether any point in the current quadrant can be within epsilon distance from the potential core point. However, for many distance metrics, creating the candidate list of points using the conventional way, which is hypersphere-based collision detection, is quite complex and complicated. And this causes the tree traversal bottleneck and makes the asynchronous interface have a big effect on the system. So as you can see in the figure on the left, instead of hypersphere, Durin uses a bounding box, which is just based on the simple larger than comparison and is a whole lot faster than using a hypersphere. Bounding box-based collision detection may cause some unnecessary computation than hypersphere-based one, but I will show the leaders that prioritizing to minimize tree traversal overhead is much, much important than just focusing on the trivial unnecessary computation at the evaluation section. Okay, then from now on, let me focus on our evaluation setting in the following result of Durin's prototype. We used the Xilinx U50 data center accelerator card plugged into a desktop-class computer with a 12-thread i7 8700 processor and 32 GB of DRAM. The FPGA card was plugged into the host machine via a PCIe Gen 3 by 16 connection, where our framework was able to achieve a steady-state transfer rate of 9.1 GB per second. And for the software comparison, we used a much more powerful and costlier server class computer with a 32-thread Xeon Gold 6148 processor. This table shows the chip resource utilization breakdown of Durin on the U50 FPGA, and all components were synthesized to be the 300 MHz timing. Because one decompressor matches with two distance calculation engines, so in the case of Hypersine calculation, 16 Hypersine calculation engines with 8 decompressors can be fed to U50 FPGA, and the bandwidth of this setting is going to be up to 38 GB per sec. In the case of Euclidean distance, 32 Euclidean modules with 16G FPE decompressors could be fed to U50, and the bandwidth is going to be up to 76 GB per second. And we actually illustrate the resource utilization of our DB-Skin control logic implementation, which is used to evaluate the performance of a conventional accelerator architecture, which implements DB-Skin control logic in the FPGA fabric instead of on the host side as Durin does. I will show the software comparison with other state-of-the-art clustering tools first. The upper side table contains the data set we used for the evaluation, and we used small-sided real-world and synthetic data sets because of very slow software performance without acceleration. And then for the naming, Durin N means our own software version of Durin without quadtree index, and Durin Q also means our own software version of Durin with a quadtree index. And this graph is normalized to Durin N. As we can see in this graph, no state-of-the-art clustering tools can support as good performance as what Durin shows, even if it does not use any acceleration scheme yet. And I wanted to underline that how the indexing scheme is important for the large and low dimensional data clustering, and also wanted to underline that our own software already has very reasonable elapsed time-wise performance. To evaluate end-to-end performance, we used two open-source real-world geospatial datasets, and these two figures illustrate the performance of Durin using a single U50 FPGA, normalized against the software implementation using R32 cores in the system, with Hilberstein and Euclidean metrics respectively. Each line represents a different minimum point count threshold value for leaf nodes of the quadtree, and the x-axis represent different epsilon values. And we used a fixed bit budget of 12 bits for each floating point value since it was a safe, error-free configuration. As we can see in the graphs, thanks to having configuration stress value, GFPE compression, and asynchronous interface, compression works very well, and Durin consistently demonstrated very high performance relative to the 32 thread software implementation during Q, as long as the configurable threshold value is 32 or larger. And this graph shows both the performance and power efficiency of our Durin compared to the 32 thread-based software implementation under the best configuration setting. During on desktop class computer with a mid-range FPGA consumes 195 watts total, and it costs about $4,000. And in the software implementation on the server class machine, it consumes 420 watts total and costs about $10,000. So Durin outperforms by up to about 20x performance and about 40x power efficiency. This graph shows the relative performance benefits of Durin against the conventional accelerator architecture, which implements both the Deviskin algorithms control logic and the distance calculation engine in the accelerator. And we give the best situation to the conventional architecture that it has a highly optimal index structure, which only requires one off-chip memory access to obtain the leaf. But actually, in reality, the quadtree data structures had a height of 10 plus level at least, and it requires at least 10 plus off-chip random memory accesses. So even if we gave the best scenario to the conventional architecture, it suffers from single off-chip index access, leaf-encoded random access, and limited resources for the distance calculation because the controller takes away valuable resources from the computation algorithm distance calculation engines. So this results in the Deviskin controller having access to only up to 2 gigabyte per second of HBM bandwidth because of the random accesses, and also results in fewer distance calculation engines being placed on the accelerator. So Turing proves itself the best way of accelerated clustering by demonstrating 2x higher performance compared to the conventional architecture. So besides providing the fastest and the most power efficient real-world low-dimensional clustering, Durin adds a new way of software-hardware co-optimization to the big data field. Thank you so much.